So welcome to Community Conversations. My name is Liz from the Dfinity Foundation. This is an opportunity for you, the community, to hear from contributors within the internet computer ecosystem, as well as ask them questions live. So in this talk, staff engineer Roman Kashitsin will view the internet computer through the lens of a distributed system design. As most other blockchains, the IC achieves fault tolerance using a strategy called state machine replication. We'll take a close look at some design choices that make the IC fast, scalable, and secure. And with that, I will hand things over to Roman.
Thanks, Liz. Hello, everyone. My name is Roman, and today we're going to talk about replicated states. So the plan today is to first take a look at state machine replication, introduce some concepts required to understand the model. Then we'll look at state trees and certification. If you heard about chain key technology, this is related to this. And last point will be looking at state synchronization, which is a process which allows nodes exchange states directly and speed up catching up significantly. So yeah, why should you look at this? Why should you watch this video? It's a tough question. You don't need to understand any of this to be able to write scalable applications on the internet computer. But I think it's very useful to understand like what makes internet computer fast and scalable. Why can you trust that like new nodes can be added easily in the future? And the second point I would like to make is that if you have at least slightly better intuition about state trees and certified variables at the end of the talk, I think my goal will be achieved. It's a pretty interesting topic, I think, and yeah, I hope I will make it a bit clearer, like the design choices behind state trees and certification. Yeah, so let's talk about state machines first. So if I say that I have a state machine, what I mean is I need to define a few things first. Like, what do I mean? So state machine is like theoretical construct, like computation model. And if I want to talk about state machines, I need to explain like or define what the inputs of the state machine are, what the outputs, what's like internal state, and what transition function is a function taking like an input state and producing a new state of the machine, and what the output function is. So given like the state, what's the output of the machine? So I think many of you saw this picture before with protocol layers, and I view these protocol layers like it's partitioned into two parts. The lower part with P2P layer and consensus, from like in the context of this talk, their main purpose is producing inputs for a state machine. So the input is a block or sequence of blocks. So the main purpose of consensus, in the context of this talk, is basically producing inputs for our state machine and making sure that those inputs are the same on all the replicas. Yeah. So, and the upper layers, which we call message routing and execution environment, their main purpose is basically implement transition function. You have the block, you have some internal state of the replica, and basically the protocol defines how you take the block, take the state, and produce the new state. So it's like a transition function of the state machine. So when I say replicated state or state, what do I mean? What's the actual state of the machine? So it's probably helpful to see the state as like partitioned in two main parts. So one part is system state, is what the replica needs to operate. for example, like queues, which you call like subnet queues. When you install a canister, it doesn't exist yet. Like the canister to be installed is stored in the queue, right? And if you send the request to internet computer, the response is stored in a, what's called like state ingress history or request status as like buffer. This is also part of the system state. It does not belong to any canister. So this is like one partition of the state. Another part of the state is actual canisters. So when you install a canister, it has some WASM module, has memory, stable memory, queues for various like input queues, output queues, so on. So like two big parts. So all your canisters are stored in some state. I think I forgot to mention that we have like, I'm talking about one subnet right now. So as you know, the internet computer is partitioned into many subnets and they have separate states. So all the nodes in the same subnet, they have more or less exactly the same state and exactly the same inputs, but nodes in different subnets have different states and different inputs. So yeah, so let's look at what we have, what we like discussed so far. So we have blocks on the pictures like squares with B1, B2 labels. And like blocks, they kind of form like linked list based on hashes. So like this is the blockchain. And we have states, which is like those blobs of data with canisters and so on. So when we just start the subnet, we don't have anything except maybe like minimal system state in there. And how the system operates, we have like this ICP protocol. We get some blocks from consensus. We take the state, which we had before, apply first block, get the next state, get the next block, apply to the previous state, and like we have like a thread of states. And one thing which I haven't discussed, like mentioned before, is from time to time we want to be able to like dump the state into what we call checkpoint, is like snapshot, persisted snapshot of the state. So state, you can think of it as like a memory data structure. And checkpoint is basically on-disk representation of this structure. So I think the only thing that we haven't mentioned yet is like what's the output of the state machine, and we will look at it like in a second. But first, I need to talk a bit about threshold signatures because this is important for the like next discussion. So if you heard about chain technology, it's the same, like chain key technology, it's basically the same thing. So if you have like nodes in a subnet, they all receive what we call key shares. So the idea here is that you can, every node can sign some piece of data with its own key share, and then you can combine those signatures together to get a subnet signature. So the clients need to have what's called like public subnet key. And this is just like one key. So if you have like basic understanding of asymmetric like encryption, you have like private key and public key, right? You encrypt things with the private key, and you can, or sign with the private key, and you can verify the signature with the public key. So in this model, the private key is split into small pieces and distributed to various nodes. How exactly it happens, it's not very important for our discussion, but there is a secure protocol to do it. So the departure point for us is that we have n nodes on the picture, n is equal to 4, and they all have key shares. Yeah, and so you have 4 private key shares and one public key. So Ian, if you want to say that like subnet produced some output, like every node on a subnet signs something, like typically hash of some value with its own key or key share. And then there is a way to combine those pieces together to produce value signed with the full key. So no node has the full key at any point in time, only some share, and only by communication they can construct the full signature. So the analogy I have in mind when I think about it is like puzzle pieces. We want nodes to be able to construct like a coherent picture out of like jigsaw puzzles pieces, and we distribute different pieces to different nodes so that any three of those nodes can combine the full picture, but like two or one node they cannot. And if you like sign something else, you don't get a coherent picture. So if you sign a wrong hash, for example, you won't get nice blue jigsaw puzzles. You'll get like dark gray or something like that, and they won't form a coherent picture. Or we can also think of it like as a key split into multiple pieces, like you have a box with 6 keyholes, and like different nodes have different sets of keys basically, and only by communicating they can construct like lock the full box. Yeah. So okay. Now let's talk about outputs. So let's say we send a message to the internet computer. We want to like update some data and get a result for like I don't know, transfer tokens and get like the current balance, something like that. So how do we get the response, and how can we trust it? So one way would be just you allow anybody to look at the state, right? Because the output of every request is in the state as well. So you can just take the state, hash it in some way, and sign the hash of the state with some, like using the threshold signature scheme, using like the consensus. And that's it. Like, and if you want to verify that your response is like X, you look at the state, check the hash of the state, and if it matches, you can trust the value. But the problem is, if you're a client and you're only interested in your own result, you still need the whole state to verify the result. So what would be nice is it will be great to have like some scheme to allow clients to zoom into the state and see like one small part of it, and like do not care about the rest, all the other pieces of the state, and still be able to verify. So somehow we compute just one hash, and we allow you to zoom into this like state, look at a small piece of it, and still be able to verify that this small piece of the whole picture is authentic, even though you only signed like the whole big thing. And the how we do it is we construct what's called Merkle tree. So we represent the state. I mean, internally it's just a data structure, some complicated data structure, right? But we construct like a different view of this data structure according to the specification. And the view is like a tree, and you can think of it as like more or less like a JSON object. So like the root is like basically the root object, and then every edge is like a field in the main object, and yeah, and so fields are always mapped to either blobs or other objects. So basically, for example, if you certify some piece of data in a canister by calling like certified data, a system API call, it's populated in a tree, or in the state, and then it's mapped in a tree to path like canister, then your canister ID, and then certified data, and the blob. If you send the request and the system produces some reply, it goes to like request status, request ID, which is like this long hash computed according to the spec, and then like reply and the like actual blob of reply. And the different state machines, like on different subnets, they communicate through cross-net communication protocol. And this also relies on those states. So basically, this state is like public view of internal data structure. And this is like the output of our machine. So our machine, if we go back to this picture with blocks and states, the output of the state machine is this tree signed by the subnet. Yeah, so just to reiterate, we get some state after processing the block. We construct a Merkle tree based on this state according to the like specification. We get the root hash of this state, and then we collect like threshold signature on it. And from now on, you can run arbitrary number of queries on the state, and you only need to talk to one node because it has like the threshold signature, and you can trust it. So it's you don't need to like send 5 requests or like 3 requests to different nodes to be sure that you have authentic data. Just like the presence of signature guarantees authenticity. So let's look at an example. So let's say you send a request to the internet computer, and then you want to get a reply. And the way it's done in the public specification is like you send a read state request to the internet computer, and you specify the path in this tree. You say like, I want to request status, use request ID, and then let's say reply. So what will be the output of your request for read state request? So the system will look at the path. It will start with the tree head, and then it will follow the path you specified or like set of paths. And everything which is not in the path will be replaced or pruned with hashes of whatever like happen to be on the left, on the right. So you won't see the full state or the full tree, all the things you don't need to care about. Maybe you don't even like have permission to look at them. All these paths will be replaced by just hashes. So the reply will be like relatively small. The tree state can be huge, like with like hundreds of thousands of requests in there, right? But you will only see like a small portion of it, just the data you wanted to see, and everything else will be pruned. But you can verify the authenticity of the data by like computing the root hash of the Merkle tree and comparing the hash against the threshold signature. Yeah, now let's talk about the state transfer. It's technology which allows nodes to exchange states directly. So, sorry. Let me first explain why do we even need that. So let's say we want to add a new node to the subnet. For example, we want to exchange the extend like the computation capacity, or we want to replace one node which was down, like became down, or like there was a flood which destroyed the data center. I don't know. We want to add a new node. So in order to participate in the protocol, the node needs to be up to date. It needs to have the latest state to be able to process blocks and propose new blocks. So one way for catching up will be just to get all the blocks from the very first one and replay all of them from the beginning. Because the protocol is deterministic, right? You should get exactly the same state. Unfortunately, this may take quite a lot of time. And in internet computer, like the computation, amount of computation is quite big. And if you have like a fast subnet, like replaying blocks might take basically approximately the same amount of time as like playing new blocks. So you will always be behind no matter like how hard you try. Well, maybe you will be slightly better because you don't need to participate in consensus and wait for blocks. But if the subnet is moving quickly, it's always like a moving target for you. And just to give you like a perspective how long it takes to replay the blocks, if we take NNS subnet, which was running like for a few months, now it takes about like 15, 18 hours to replay blocks from the very beginning. And state sync can be done in like 2 minutes. So it's like huge speed up comparing to replaying blocks. Okay, now we know why we want to do the state transfer. Let's take a look how it's done. So from time to time, the replica takes the state it has and persists it into a disk, like into a folder, basically. So what we have is like a set of files, and the replica divides those files into chunks, like pieces of like relatively small size. Because, for example, memory can be huge, like multiple gigabytes of data. So it divides those files into small chunks. What it does next is computes something called manifest. So manifest is basically like a data structure defining, okay, these are all the files, like this defines every like size of every file and the hash of every file, and then also all the pieces of every like of all the files with hashes of every piece. Basically, you can think of it as like, okay, which files do I have, and which pieces of files do I have, and you can, if you have a manifest and you can trust it, when you receive like a piece of file, you can check that this is authentic piece of the file because the hash matches to what's specified in the manifest. Sorry. So what happens next is replica computes like the hash of this manifest. So like you can think of it like a root hash of the whole state. And the replica advertises to other nodes, I have this state, like it's state number 9, and this is like the hash of my state. So the next step is consensus, like as a subsystem on a single node, not like a consensus among all the nodes. Consensus takes this hash and constructs an artifact called ketchup package. For the purpose of the discussion, it's enough to know that like the ketchup package has just like the full hash and the threshold signature of this full hash. So basically, it's like an artifact describing another artifact. So one artifact will be like this state, and it has like this hash. Another artifact is like ketchup package, saying that like there is like the subnet agreed that the state at height 9 has this hash, and this is like the threshold signature of the hash. So why do we need it? Why do we need the ketchup package? And the reason is that like if you just see that, let's say you want to catch up, right? You add a new node, and this node like looks at the network and wants to get the latest state. Like how does the node figure out which state it should be using? Especially if like you can see like, okay, some nodes advertise that they have state at height 9 and they have this hash. Some nodes advertise that they have the same state with a different hash. Like whom can you trust? And ketchup package is basically like the thing which allows you to figure out whom you can trust. So when a new node joins the subnet, it first looks at the ketchup packages like artifact. And when it sees like a valid one, it says, okay, there is a state number 100. This is like a hash of the state, and this is a threshold signature. The consensus is like part of the protocol on a single node, not consensus among all guys. So this consensus module on a single replica sees this ketchup package and says, okay, I can trust this hash because it has like threshold signature on it. So the majority of the network, they agreed this is like the right hash. So I can trust this hash. What consensus does next is like compares this state height to local state height. Let's say we were out for some time. So we're not adding a new node, but we were just down for some time. I don't know, the like machine rebooted and network moved on. So we start and we have local state, actually, and it's like state number 9, and we see the ketchup package with state number 100. So what the consensus does is like, okay, I'm missing out. My state is 9, and this network already at state number 100. So I better get the new state. Then it goes to the state machine, which is also a client of P2P, and says like, can you please fetch and unpack the state number 100? By the way, make sure that the hash is like the one specified in the ketchup package. And the state machine, like, okay, it remembers the state it needs to fetch. And when it sees like the advertisement of the states, it compares the hashes. And if the hash is the right one, it goes on to fetch the actual state, like the set of files. So let's take a closer look at how the fetch is working. So as I mentioned before, let's say we already have some state. Maybe it's not like the very fresh one, but at least we have something. So the protocol designed in a way which allows us to take advantages of what we already have. So if we say we were out only for a brief moment, we don't need to fetch like gigabytes of the state. We can only change, we can get just what changed in the meantime, which is typically much faster, like seconds, not minutes, or like tens of minutes. So on the left on the picture, we have a node which is up to date. It constructed checkpoint number 100, which has some files, and it computed manifest, advertised it. On the right side of the picture, we have node, which is trying to catch up. It has local state like 9, and it wants to get to the state 100. So first thing that the node does, it fetches the new manifest, manifest number 100. Then it compares the new manifest to the previous manifest and sees, okay, which files were added and like which chunks of those files were modified. Let's say that like the queues file didn't change at all, and in the memory, like memory was extended, it added like a new chunk, and then like chunk number 0 was modified and chunk number 1 stayed the same. So how we can proceed, we can copy the queues as they are. We can copy like first chunk of the memory into like the new checkpoint. Then we need to fetch chunk number 0 from the node which is up to date, and chunk number 2 from the memory from the node which is up to date. So we kind of do things and combine the new checkpoint out of pieces. Yeah, and once all the chunks are in place, we can just, okay, we have everything, and we can unpack the state basically, or load it from memory or from disk, I mean, and then start executing blocks. Block 101 in this case. Okay, so yeah, how can we trust the pieces that we fetch from the up-to-date node? Because the nodes can be malicious, right? And because we have the manifest number 100, it specifies like hash of every piece of every file. And we hash the manifest itself to check like the hash that we're trying to fetch. Can we trust this manifest or not? And then every time we receive a new chunk, we can actually validate it if it's like has correct hash or not. So we can trust that by the end of this procedure, whatever state we have is authentic. So another thing I wanted to mention is that we can fetch pieces of the state from multiple nodes in the same time. So it's sort of like transmission, like you can fetch pieces of the state from like all the nodes in the subnet who have the state in parallel, which is typically much faster than fetching from the single node. So just to like summarize everything we learned so far, so we have you can view the internet computer, or rather one subnet of another computer, as a replicated state machine. The inputs of this machine are blocks. The states of this state machine is like system state, statuses of your requests, and canister states. And everything is updated. Like the computation proceeds according to like this protocol. And at every round of execution, after every block, the machine produces state trees. Those state trees are certified but by the consensus. Basically, we get the root hash and gather a threshold signature on it. On the picture, I'm like represent those certifications as like stars the states get. So all these read requests, for example, they go to the latest certified state, not just the latest state you have. And from time to time, we produce something called checkpoint. Checkpoint is like on disk representation of the state, which allows other nodes to catch up. And consensus builds artifact called CUP, or catch-up packages, which are also certified. And those artifacts are used to enable state transfer in a secure, authentic way. And I will be glad to answer any questions you have.
Great. Thank you so much, Roman. So if anyone has questions for Roman, feel free to let us know or drop in the chat. Or I know that sometimes for some people, it takes some time to digest the talk. So if you wanted to reach out to me on Twitter after the fact, I am at WizWang, that's WHIZWANG, and I can field questions to Roman then. So Roman, I'm seeing that there aren't any questions in the Q&A or in the chat. So I think this might have to be more of like a retroactive Q&A kind of deal, unless there's a last minute question that comes in.
Yeah. I guess it's just short notice, and we only published the talk yesterday, the announcement. Yeah.
Cool.
Great. I will be glad to answer any questions people have later on, like in YouTube or whenever.
Sounds good. So thank you so much, Roman, for this enlightening talk. And if there are any questions after the fact, I will make sure to field them over to you, and we can post them in a public place, such as the forum or on Twitter.
Thank you.
Cool. Thank you, Roman. Bye.
Have a nice day. Goodbye.